All right, so in the last video, we solved this non-homogeneous system here, and we got a general solution and wrote it in parametric vector form, and I asked you to look at the solution. Do you guys notice anything familiar here? All right, so maybe I'll do like a little arrow here. It looks familiar. All right, actually, it is the solution to the homogeneous system. Let me find that for us. All right, x3 times -1, 1 is the solution for the homogeneous system for that matrix. All right, so what is always true is that for our non-homogeneous system, we can write it as P plus x3 times V, where P is the 2, 1, 0, and V is the -1, -1, 1. Okay. All right, so note, okay, remember, I said this looks just like the solution to our homogeneous system. So let's actually get that in writing so you can go back and read that. So it looks like, the solution to AX equals 0. And this letter P that I just named for this vector in front is called a particular solution. Of our non-homogeneous system, AX equals B. All right, so let's visualize these two. I'm going to do it in 2D instead of 3D because 3D is hard for me. And I think you'll get the picture just from 2 dimensions. All right, so let's say we have this situation, P plus X3V, something like this. Okay, so let's visualize in 2D, even though this should be 3D because we're in R3. But we're going to do 2D because 3D is hard to draw. Okay, so I'm going to draw 2 axes. Let's say this is my x1, positive side, negative side, x2, positive side, negative side. All right, and then let's just say we have our vector v. So kind of like before, but we're going to do it in 2D. So let's say this is not the solution, but let's say this is our vector v. All right, so P, remember P plus anything times this one. So when we're adding vectors, we're just translating, right? We're just going to shift it up, right? So our P is going to do the shifting. So let's say we shift it up. This is our vector P. And then we add V to it. So I'm going to try to draw something that's the same slope. We got V on top. All right, so if we draw a line that goes through this V here, this represents all of the solutions of our homogeneous system. All right, so remember our homogeneous system, the solution was just x3 times V. All right, so that's the solutions. And then if I draw a line here, these are going to be all of the solutions of our non-homogeneous solution system. All right, so notice how they look on the graph. The homogeneous solution set is going to be parallel to the non-homogeneous solution set. Sorry about that. All right, now let's write a theorem. Let us suppose that AX equals B is consistent. So we were able to find a solution. And that P is one of those solutions. So it's a particular solution. Then P plus some vector Vn is also a solution. Of AX equals B if Vn is a solution of the homogeneous system. All right, and so that's exactly what we saw before. All right, this P is going to be a solution of AX equals B. However, sorry, but if we add them together, it's also going to be a solution, only because this V is a solution of the homogeneous system, and it's always going to be true. All right, so I'm going to write us an example, and then I'm going to ask 2 questions of us that we'll answer, and that's where we'll end. All right, so here's the example. We're going to let A be a matrix. It's a 3 by 3. Excuse me. Same one we've been working with in this section. 2, 1, negative 1, negative 3, 1, 3, negative 1, 2, 2. And I'm going to row reduce it into RREF. All right, so this is just a regular matrix, not an augmented matrix. 1, 0, 0, 0, 1, 0, 1, 1, 0. Okay, so I have 2 questions for us, like I mentioned. Question number 1. Does AX equal B have a solution for any B? All right, so I want you to take a moment and think about that. Can I choose just any B that I want to set this equal to? What if when I got down here, I had a number, but zeros down here? So the answer is no. We can't just solve AX equals B for any B that we want because we don't have a pivot position down here in the 3rd place. All right, so the answer would be no, because A doesn't have a pivot position in every row. All right, I'm going to try to squeeze in question 2 on the same page. Question 2. Does there exist a B where AX equals B will have a unique solution? Could we ever get a unique solution where we just have one solution? x1 equals this, x2 equals this, and x3 equals this. All right, so note that we have free variables, so our x3 is always going to be free. So that means we're going to have infinitely many solutions. So the answer to this question is no. The system will always have a free variable because of these zeros. And that means we're either going to have infinitely many solutions or we're going to have no solution, right? If something strange happens over here. So we can have infinitely many solutions or no solutions, but we won't have a unique solution with this kind of setup. All right, so that is the end of this section.